Right now, at this very moment, scientists around the world are working on something that most people would call impossible. Content reference, oocyte 0, index equals 0. They are trying to take the power of a star and bring it down to Earth. Not as a dream, not as a theory written in a textbook, but as a real, working machine that could one day power your home, your city, and your entire country. And the most exciting part? We are closer to making that happen than we have ever been before. The breakthroughs happening today in laboratories from France to California to the United Kingdom are not small steps. They are giant leaps. And the world is finally starting to pay attention. To understand why this is such a big deal, you first need to understand what a star actually is. Our Sun, the giant glowing ball of fire sitting 150 million kilometers away from us, is not on fire in the way a candle or a campfire is. It is not burning wood or gas. Instead, deep inside the Sun's core, atoms are being smashed together with such incredible force that they merge into new atoms. This process releases a mind-bending amount of energy. Every single second, the Sun converts around 600 million tons of hydrogen into energy. That energy travels across space and reaches us as sunlight, warmth, and life itself. This process is called nuclear fusion, and it is the most powerful energy source in the known universe. Every crop that has ever fed a family, every storm that has ever crossed an ocean, every drop of oil that has ever been burned in an engine, all of it traces its origin back to this one reaction happening at the heart of our star. For decades, scientists have looked at the Sun and asked a very simple but very ambitious question. If the Sun can do this, why can't we? Why can't we build a machine right here on Earth that does the same thing? If we could harness even a tiny fraction of that power, we would never have an energy problem again. We would not need to burn oil, gas, or coal. We would not need to worry about running out of fuel. The oceans are full of hydrogen, and hydrogen is the fuel of fusion. The supply would be practically endless. One glass of seawater contains enough hydrogen to power a house for an entire week if it could be used in a fusion reactor. The potential is almost too large to fully understand. But building something that replicates the heart of a star is not simple. Inside the Sun, the pressure is so extreme that a teaspoon of its core material would weigh nearly a kilogram. The temperature at the Sun's center reaches around 15 million degrees Celsius. These conditions are what force hydrogen atoms close enough together to fuse. On Earth, we cannot create that kind of pressure. So instead, scientists have to make the temperature even higher. To get fusion happening in a laboratory, you need plasma heated to around 150 million degrees Celsius. That is 10 times hotter than the core of the Sun itself. And you have to sustain those conditions long enough for a meaningful number of fusion reactions to actually take place. Plasma is not something most of us deal with every day. It is a fourth state of matter, beyond solid, liquid, and gas. When you heat a gas so much that the electrons are ripped away from their atoms, you get plasma. It is a soup of charged particles moving at incredible speeds. The Sun is made almost entirely of plasma. Lightning bolts are plasma. The flame of a candle contains a tiny amount of plasma. But the kind of ultra-hot, dense plasma needed for fusion is something we can only create in very special machines. Creating it is one challenge. Keeping it stable and hot long enough for fusion to happen is an entirely different one. The challenge of harnessing fusion energy on Earth comes down to one very practical problem. 47. How do you hold something that is 150 million degrees hot? How do you hold something that is 150 million degrees hot? No metal, no material, nothing on Earth can physically contain something that hot. If the plasma touched the walls of any container, it would immediately cool down and fusion would stop. It would also destroy whatever it touched in an instant. So scientists had to think of a completely different way to hold the plasma without actually touching it. The solution they came up with is elegant and fascinating. They use magnetic fields. Invisible forces, perfectly shaped, to wrap around the plasma like a cage made of pure energy. Because plasma is made of charged particles, it responds to magnetic fields. Powerful magnets can push and pull plasma, bending its path and holding it in place without ever making physical contact. The most successful design for doing this is called a tokamak. A tokamak is a large, donut-shaped machine surrounded by powerful magnets. The plasma flows around inside this donut shape, held in place by the magnetic field, getting hotter and hotter until fusion begins. The biggest tokamak ever built is called ITER, currently under construction in the south of France. It is the size of a 10-story building and involves contributions from 35 countries. When it is finished and running, it will be a landmark moment in human history. For many years, the problem with fusion machines was simple. They used more energy to heat the plasma than they ever got out from the fusion reactions. It was like spending $10 to earn $5 back. Not very useful. But in December 2022, something changed that rewrote the story completely. Scientists at a research facility in California fired a set of the world's most powerful lasers at a tiny pellet of fusion fuel, smaller than a pea. The result was extraordinary. For the first time ever in human history, more energy came out of the fusion reaction than was put in to start it. The reaction produced 3.15 megajoules of energy from an input of just 2.05 megajoules. It was a small margin. But it was a crossing of the finish line that scientists had been chasing for over 70 years. The room where it happened reportedly went completely silent for a moment before the celebration began. The room where it happened reportedly went completely silent for a moment before the celebration began. Then, in late 2023, a different machine in the United Kingdom called the Jet Reactor broke its own world record. It produced 69 megajoules of energy from just 0.2 milligrams of fusion fuel. To put that in perspective, 0.2 milligrams is a grain so tiny you could barely see it. Yet it released enough energy to power a small town for a brief moment. These numbers are still small compared to what a full commercial power plant would need to produce. But every record broken is proof that we are not just dreaming. We are doing it. We are getting closer, step by step, to harnessing the power of a star for real, everyday use. Private companies have also entered this race in a way that was unthinkable just 10 years ago. Commonwealth Fusion Systems, based in Massachusetts and backed by some of the biggest names in technology, is building a compact tokamak using a new generation of ultra-strong superconducting magnets. These magnets are so powerful that they allow the machine to be far smaller than ITER, potentially cutting costs and construction time dramatically. Content reference, Oocyte 0, index equals 0. The company believes it will have a working commercial fusion plant online by the early 2030s. Another company called Helion, based in Washington state, is taking a different approach entirely. Instead of using the standard combination of hydrogen isotopes, Helion uses a reaction that produces energy in a way that can be converted directly into electricity, skipping the need for steam turbines altogether. Helion has made the bold claim that it will supply electricity to Microsoft data centers as early as 2028. Now, it would be dishonest to say that all these problems are solved and that fusion power is guaranteed. There are still real challenges. The fuel used in most fusion reactors includes a hydrogen isotope called tritium, which is extremely rare and difficult to produce. Neutrons produced during fusion reactions can damage reactor walls over time, meaning components need to be replaced regularly. And scaling up from a laboratory experiment to a full power plant that produces electricity reliably, cheaply, and safely is a massive engineering challenge that will take years of careful work. Each solution in fusion tends to come with its own new set of questions. That is the honest truth, and anyone who tells you otherwise is oversimplifying. But here is the thing. None of those challenges are fundamental barriers anymore. They are engineering problems. And humanity is very good at solving engineering problems. We built airplanes. We put humans on the moon. We created the internet and connected billions of people across the globe. The fundamental physics of fusion is now proven to work. The question is no longer whether fusion can produce energy. It can. The question is now how quickly we can build the machines, train the engineers, and solve the remaining practical problems to bring this technology to the world at the scale it deserves. The timing of all this could not matter more. Our planet is getting warmer. The burning of fossil fuels is changing the climate in ways we are already starting to feel in every corner of the world. At the same time, the global demand for electricity is rising every single year as more people gain access to power, and as technology requires more and more energy than ever before. We need a clean, powerful, and reliable energy source at a scale we have never needed before. Fusion fits that need perfectly. Its fuel comes from water. Its main byproduct is helium, a useful gas. It produces no carbon. It does not create the long-lasting radioactive waste that comes from today's nuclear power plants. The sun has been powering our planet for 4.6 billion years. Every plant that ever grew, every drop of rain that ever fell, every gust of wind that ever blew was ultimately powered by that distant nuclear furnace in the sky. And now, for the first time in history, we are not just receiving the power of a star from afar. We are building machines that can make that same power right here, on the ground, under our control. We are harnessing the power of a star. Not in full yet. Not at commercial scale yet. But we are closer than we have ever been before. And for the first time in a very long time, the scientists working in this field truly believe that the wait may finally be nearly over. The dream that started with physicists looking up at the sun over a century ago, wondering what made it shine so brightly, is on the verge of becoming the most important technology our civilization has ever developed. We are close. And close, right now, is everything.